Hi there, students. Maybe it's good morning, maybe it's good afternoon, maybe it's good evening. So whatever you happen to be watching this lesson, I'm glad you were able to join me. This is Mrs. Brunk, and Algebra 2. We're going to be looking at Lesson 5.2 today, which is graphing polynomial functions. So our most recent lesson, we explored the graph of x cubed and different transformations. So that's the basic cubic parent function, and then any transformations of that. And in today's lesson, we're going to see if we can go a little beyond that. And our essential question is can we sketch the graph of a polynomial function that is in intercept form? So first thing I did is I went and graphed each of the parent functions for x, x squared, x cubed, x to the fourth, x to the fifth, and x to the sixth. And I have them next to each of these functions. We'll just kind of go through each one of them and identify some characteristics. Now, the only one I did not graph is y equals x, which is that basic linear function. Actually, I'll just graph that real quick. And you know, y equals x is in slope-intercept form. It's just that the y-intercept is 0, right? So that crosses at 0, and it has a slope of 1, rise 1, run 1, rise 1, run 1. Maybe go down 1 and left 1. And when we connect, it looks something like this. So when we think about a line, its domain is the x values, right? And we think left to right when we look at the graph. So going left to right like this, you can see that the graph goes on forever in either direction. And so that's all real numbers. And if we wanted to write it, we could use interval notation, or we could simply just use the all real number symbol. Now the same with the range. The range, you go up or down like this, okay? And we can see that that goes on forever. So again, all real numbers for the range. Our end behavior, our end behavior, which means what's kind of going out the ends of the graph. And you can see that as you're going to the right, the graph is increasing. So it's going towards positive infinity as I'm going towards positive infinity for the x's. So in other words, as I'm going to the right, my graph's going up. As I'm going to the left, my graph is going down. So that would be on the other end. Now, if I wanted to look at the graph of y equals negative x, that would look almost the same. The only difference is that graph, in terms of, it's the same line. It goes through the origin and all that. It's just that instead it has a negative 1 slope. It's like a reflection over the x-axis. So it would look like this. So in that bottom table here, the domain and the range are not changing at all. So our domain is still all real numbers. But this time our end behavior goes the opposite way. So this time as I'm going towards positive infinity for the x, the graph's going down. So that means I'm going towards negative infinity as I'm going to the right. And as I'm going to the left, it's going towards positive infinity. Of course, so that reflection just basically caused the ends of the graph to go in opposite directions then. So let's go back now. Let's look at the graph of x squared. So we've studied that in a lot of detail. So this is x squared right here, right? And that's the parabola, right? And it's in its base position. We know that the domain is all real numbers because you can square anything, right? But the range for the parent function here is y is greater than or equal to 0. Because notice the graph only exists up here, right? It doesn't exist below the x-axis at all. When we look at the ends, see the ends both point up, right? So as I'm going to the right, the graph is going towards positive infinity, and as I'm going to the left, it's going towards positive infinity. So both directions, left or right, the graph is increasing forever at the ends. If we looked at the negative x squared, so that's this graph right here, negative x squared, the domain is still the same. all real numbers. The range this time, though, is y is less than or equal to 0, because the graph is flipped down, right? So the highest it ever gets is 0 for the y. And then this time, the ends of the graph, they both go towards negative infinity. So with the linear graph, the ends always went in opposite directions, right? Because it's a line, right? And one's going to point up and the other's going to point down. But with a parabola, the branches always go in the same direction, either both straight up, if it's a positive leading coefficient, or both straight down. So what we're going to do is we're going to see those patterns repeating in some of these other functions. So we just most recently looked at x to the third. So here's a graph of x to the third power. In x to the third, we said that the domain and the range were both all real numbers. And that's because as you look left to right, the graph doesn't cut off, right, like that. And also up and down, it doesn't cut off. Just keeps going, right? So all real numbers for both of those. So the ends of the graph, notice that on the right-hand side, it goes towards positive infinity. And on the left-hand side, it's going towards negative infinity for your ends. It's pointing down, in other words. If we jump down and look at the one with negative in front of the x cubed, so that's this graph, domain and range are still both all real numbers. But now, on the right-hand side, so over here, right, the end is pointing down, so that means it's going towards negative infinity. And on the other end, on the left-hand side, it's going towards positive infinity because we've reflected the graph. Next we're going to look at, this is going to be a new one for us, is x to the fourth power. Well, this is the most basic parent function for x to the fourth power, and it's right here. This is x to the fourth power. And it looks an awful lot like x squared. Now what you're going to find is that with all these polynomial functions, as you add things to them and subtract things from them or multiply them by things, if we add more x terms, like let's say we didn't just have x to the fourth, let's say we had an x to the third term in the function or x squared or whatever, you're going to see more bends and turns. But the most basic parent function of x to the fourth looks an awful lot like the parabola, except for that you can see down here between -1 and 1, it's flatter. So it's down here, it just flattens out, and that's because now we're taking numbers that are between 0 and 1, or really, I guess, between -1 and 1, so very, very small fractions, like a half or 0.2 or whatever, and now we're raising them to the fourth power, which makes them even smaller, right? And so that's flattening out there. And but otherwise, the characteristics are just the same as the quadratic graph. So the domain is all real numbers, the range is y is greater than or equal to 0, and the ends both go up. So the end behavior is both towards positive infinity. So now looking at the one that has the negative coefficient out in front, so the reflection over the x-axis, we'd still have all real numbers. We would now have y is less than or equal to 0, because again, this graph right here, which is negative x to the fourth power, is going to behave just like x squared. And that's because it's an even exponent, right? So both ends now are going towards negative infinity. So we have 10 towards negative infinity, negative infinity. Let's go back to x to the fifth power. So x to the fifth power is this one. And this looks very much like x to the third, except for, again, you see that flattening out near the origin, because now we're raising very small numbers to even higher powers, which is making them even smaller. But the domain and the range are going to be exactly the same as x cubed. So we're definitely going to see this relationship between these two functions going to be the same. And the ends behave the same as well. Although they get there a little quicker because the power is higher, as you get further out to the right, it's going to go towards positive infinity just a little faster, and then towards negative infinity on the other end. Okay, and if we looked at the reflection, so down here, this is negative x to the fifth. Okay, and real numbers for both domain and range for this one again. But this time on the right-hand side. Now over here, as I'm going towards a positive infinity for x, my graph is going towards negative infinity. And on the left-hand side, it's going towards positive infinity on the other end. So again, you kind of see this repeating pattern when you have the exponent is 3 and 5, and then also you can see that connection between when it's 2 and 4. And that's because when it's an even exponent, it's going to behave that certain way where the ends are going to go in the same direction. It's going to have that kind of bowl effect, this parabola effect, where it's got reflection symmetry. And all the ones with the odd exponent are going to have rotation symmetry only, and they're going to have branches that go in opposite directions. So the odd exponent ends go in opposite directions, odd and opposite, right? So you could, if you had to make a prediction, although you don't because here's the graph of x to the 6th, you could say it's going to behave just like x to the 4th and x squared, and it does. All real numbers for the domain, y is greater than or equal to 0 for the range. The ends are both increasing, so both going towards positive infinity. Okay, and so we can show that all these, actually maybe if we highlighted them that would be better, or just circle them. All the yellow ones, all the even ones, if you look at, they're very similar, and those are all the graphs over here, right? Very, very similar. Just around the origin is the only thing that makes them different, and also the steepness of the branches. Whereas all the odd ones, so the odd ones, to the 5th, to the 3rd, and even the one to the 1st power, those are all going to behave in a similar way as well. So you've got that connection when the exponent is odd, the ends go in opposite directions, and the domain and range are all real numbers for both. Whereas you have a limited range on the even ones, and that's because when you're raising negative numbers to even powers, it's going to turn it positive, right? So that's why you don't have ends going in opposite directions. Okay, so kind of looking over here, we got this one last graph. That's the reflection of the one we just looked at. Right, so that's over here. This is negative x to the 6th power, and again behaves just like negative x to the 4th and negative x squared. All real numbers for the domain. Polynomial functions, you're going to see domain is always all real numbers. Okay. But the range is going to be different depending on whether the highest power is odd or even. So the range of this is going to be y is less than or equal to 0. So again, you see that repeating pattern. All the evens are similar. So we've got negative, oops, I meant to do that in yellow. Negative x to the 6th, negative x to the 4th, negative x squared, all similar. And here you see their graphs over here, right? And then all the odd ones, you got negative x cubed, and negative x to the 5th, and those are all going to have all real numbers for your domain and range, and the ends will always go in the opposite direction, with the right-hand side facing down and the left-hand side facing up for all of these. Okay, so then the other thing we need to be looking at to be able to kind of eventually put these graphs together is investigating the x-intercepts and turning points of the graph of a polynomial function. So if we think about looking at these graphs of these three functions, we have x cubed, we have x squared times x minus 2, and we have x times x minus 2 times x plus 2. We want to look at how many distinct factors does it have? What are the graph's x-intercepts? Is the graph tangent to the x-axis, or does it cross the x-axis? In other words, does it just kind of touch it but not actually cross over it? That's what tangent means. How many turning points does the graph have? How many global maximum values? How many local minimums, or local maximums? And then the same question with the minimums, global minimums and maximums. So what are those things, and and how can I answer these questions using the graph. So here's what the graphs would look like, and you can also put them in your calculator along with me. You could just do them one at a time. We'll just do the x cubed first. We kind of already know what that one looks like. So this is the graph of x cubed. And let's see if we can answer all these questions on that. So it says, how many distinct factors does f of x have? Okay, well, when I look at just the factor, there's really no way to factor x cubed. I mean, other than just saying it's x times x times x. That would write it in factored form, and it would just be 3 x's multiplied, right? But distinct means different. And so there's just, how many distinct factors does it have? It just has 1. Okay? What are the graph's x-intercepts? Well, when I look at this graph, the x-intercept is right here, and it just crosses one time, and it crosses at 0. So it crosses at 0. Is the graph tangent to the x-axis, or does it cross the x-axis at each intercept? Well, this actually does cross on through, right? It actually passes through and then goes to the other side of the x-axis. So it crosses. Okay. How many turning points does the graph have? Well, it really doesn't. It has a key point. It's kind of like weaving through that axis, but it really doesn't have any turning points. It's not changing direction at all. It was always increasing, so 0 turning points. How many global maximum? Okay, global maximum means the absolute highest point that the graph can ever get to. But if you remember, this graph continues up forever. So it actually has no global maximums at all. But it also doesn't have any local maximums either. It doesn't have like, so like if you had a graph that went kind of like this and like this right here would be a global maximum because that's as high as it ever gets to, and this would be a global minimum, or so yes, a global minimum, because that's, no, not global minimum, a local minimum, excuse me, because this thing continues on down forever, so there's no like global minimum, right? There's no lowest point it's ever going to get to. This would be called a local maximum. So it's like, it is a high point in the area. So local means like in that area, whereas global means absolute. So kind of looking back at our graph x cubed, this does not have a local maximum or a global maximum because it actually goes on forever up, and it also goes forever down. So it's got none of either one of those. So if we took this next function, x squared times x minus 2, and we entered it in our grapher, we'd get something that looks like this. And so notice with this graph, it looks like that typical cubic function, except for that there definitely is a bend and a change in direction here. Now, instead of just going like this, you know, like when it normally, the cubic function just kind of goes like this, it doesn't actually change direction. But because now we've, and we can tell this actually is a cubic function. If you think about it, you could distribute it through. It would actually be x cubed minus 2x squared. And you'll see that it's got now more bends and turns. Like I said, the more terms, lower degree that you add on there, the more you're going to get that graph to have more bends and turns and other things going on. But essentially it is still a cubic function. It's just now it's got more things going on. So when we answer this question, and this is written in what's called, this is kind of intercept form, or it's factored form, another way to say it. How many distinct factors does f of x have? Well, I see 2 factors, x squared and then x minus 2, so 2 factors. What are the graph's x-intercepts? Well, I can see it crosses or hits the x-axis here and here, so at 0 and at 2. And if you look at the factored form, x squared, okay, well, the thing that would make that 0 is 0, and then x minus 2, well, 2 would make that 0. So that's where those roots or the solutions or x-intercepts come from. And then it says, is the graph tangent to the x-axis, or does it cross the x-axis at each x-intercept? Well, here, right at this one, it actually is tangent to it. And what that means is, it's almost like it comes up and it just kind of kisses it, kind of turns back around, just quick, boom, quick kiss, turns back around and goes. just barely touches it and then goes back down and stays on the same side of the x-axis. If that's the case, then that's tangent there. And later on we're going to learn that that actually means that that root counts for more than one of the solutions. So if we have a degree 3 polynomial, we would expect to have 3 solutions. Just like with a quadratic, we could expect to have 2. We don't always have that. Here we have 2 distinct ones, but one of them actually counts as more than one. So that 0 is actually what's called multiplicity, because it counts for more than one root. So this one is, right here, is the tangent. It's tangent at it. And this one actually crosses. So we could, oop, I didn't even spell tangent right. T-A-N-G-E-N-T. And then this one crosses. Ooh, it's kind of a busy table there. How many turning points does the graph have? Okay, well the turning points now, if we look at the graph, it's every time it changes from increasing to decreasing. So right here, it changes, here, right here, it changes from increasing to decreasing, so that's 1. And then here from decreasing to increasing, that's 2. It has 2 turning points on the graph. How many global maximums? So the absolute highest point, there are none. Cubic functions will continue up forever. They also continue down forever, so there'll be no global. So we'll put global, there's 0. And global minimums, there's 0. There's not an absolute minimum this ever gets to. But you can see that there is what's called that local minimum or maximum, and it's actually where the graph changes direction, right? So it's right here. That was that point right there. Shoot. And that point right there are global max or mins. The first one is, number 1, is a global max, or I'm sorry, local. Local, in the arrow. Local max is 1, and there's 1 local min. Okay, so it's the highest point in the area. It's just not the highest point overall, and it's the lowest point in the area, like in the neighborhood. But just not, and sometimes they call them relative minimums and maximums. It means relative to the area that it's in. But absolute or global is what it means when it's the highest it ever gets. But in this kind of graph, because those cubic functions go on forever in either direction, they're not going to have global maximums or minimums. And here's the final graph. That's the graph of x times x minus 2 times x plus 2. And how many distinct factors does f of x have? Well, you can see 3. 1, 2, 3. There's x minus 2, there's x plus 2. There's 3. What are the graph's x-intercepts? Well, you can see it crosses here at -2. You can see it crosses at 0, and you can see it crosses at 2. The next question says, is the graph tangent to the x-axis, or does it cross the x-axis at each intercept? It crosses for everyone. See how every single one just actually slices through, goes all the way through onto the other side, right? Here, and here, and here. So crosses at all of them. How many turning points does the graph have? Well, turning points, you can see that it turns twice, much like the last one. Okay, it turns right here. There's a turning point. There's a turning point here. So 2. How many global, well, we said global cubic functions will have none. Maximums or minimums. There's no absolute max or min because these continue on forever, right? Either direction. So they're not going to have global. But like you think about if you had like a graph, like a parabola like this, okay, this would be a global minimum, right? Because that's as low as it ever gets to. So like parabolas have global minimums, but no local minimums. Or if the parabola opens down, it has a global maximum, but no local maximum. Because right, it's just absolute. There's not enough bends and turns to get more than one type of maximum. Now, as far as the local ones go, there is a local maximum, and it's right here. This is the local maximum right there. Oops, right there. And there's 1. And then local minimum, there's also 1, and it's right here. Okay, so this one's a local max, an LM, and this is a local, oops, I guess LM, I can't, I guess I have to do local max, and then local min for this one. So L min, local min, but no absolute max or min. Okay, so now we're going to look at some functions that are actually a degree 4. So all of these, if we were to actually multiply them all out, multiply those factors back out, they're in factored form right now. If we were to multiply those back out, they would have the highest degree of 4, so they would be quartic functions. So here's the most basic. We've already looked at that one. This is x to the 4th power. How many distinct factors? Well, you just see there's distinct factors, just 1, okay? Just x to the 4th. And how many x-intercepts? Well, you just see 1, right? You just see it crosses, again, at the origin. This is the parent function, so it's the way they all do. They cross at the origin there. So that's crossing right there at that spot. And that x-intercept is actually tangent. So I'm going to just write tan. Because, again, the graph doesn't actually pass to the other side of the x-axis. It just touches it and then turns right back around. So it does create an x-intercept, but it turns back around. And actually, it turns out when we learn about this thing called multiplicity, that solution, that x-intercept, actually accounts for 4 of the total 4 solutions that a quartic function could have, or quartic equation. And that's, you know, how it's kind of flattened out there. It's almost like it's kind of spending extra time there near the origin, and so it just counts for more solutions because it doesn't just kind of pass through really quick. It kind of takes its time, and then as it's turning back around, it's spending even more time there. So how many turning points are there? There's just one, just that one spot at that 0. It turns from decreasing on this side, right? On this side it's decreasing, and on the other side it's increasing, right? So one turning point. How many global maximum values? There's none. There's actually no maximum values at all. This thing has a minimum, has minimums, but it has 0 of either one. So G global and local, no minimums, or no maximums, excuse me. But it has a global maximum. Oh, why can I not say this? I'm so sorry. A global minimum of, there's 1. That's the lowest it ever gets, but local minimum, there's none. So that actually counts as the absolute lowest point right here that it ever gets to. And then there's no more bends and turns, so there's no more opportunities to create maximums or minimums of any kind. Okay, so I know these are kind of hard to see, but I think you probably see them well enough. So this next one is x cubed times x minus 2. So how many distinct factors? That's what this graph looks like. There's 2 distinct factors. I see the x cubed and there's the x minus 2, right? What are the x-intercepts? Well, this crosses here. I already got a dot on the one spot right here. And then it crosses here. So they're at 0 and 2, which if you look at the factors, it makes sense why that is. Oops. Now, it asks if the zeros are tangent to, or they cross the x-axis. Well, they cross in both cases. So they actually cross on through. This one, it kind of bends through a little bit, but this one just cuts straight through. And again, when we talk about multiplicity of roots and what they count for, that one that bends through actually is going to count for more solutions. That actually accounts for 3 solutions, which if you look at that factor that 0 comes from x to the 3rd power, it makes sense that would count for 3 of the solutions, and then the x minus 2 counts for 1 solution. Again, that's kind of, we're going to talk more about that down the road, but just for now, you just need to know that both they cross through because they have points above that x-axis, and then after they hit the x-axis, then they have points below it. So that's crossing through. They're not tangent too. How many turning points? Well, technically on this one, there really is only 1 true turning point, because this graph is actually, it's decreasing like this over here. And then it kind of bends through the axis, but it still is decreasing here. And then it turns around and it goes the other direction here. So then it starts at that point and it starts to increase. So there's just one turning point. It's right there. So one turning point. And if I just wanted to look at that point and classify it as some sort of max or min, it's clearly a minimum and it's actually a global minimum. So there's one global minimum, and I'm just going to list that because that means there's 0 of either one of the max. There's no max, so we could just say none for this. And there's one global minimum because that's as low as it ever gets. You know, it's not going to turn back around, right? And so that's as low as it ever gets. So that would be considered a global minimum. There is no local minimum. Okay, there's no minimum in the area. There's just one absolutely. Okay, next one. So you can see that the more factors that we have here, so again, if we expanded this back out using FOIL and distribution, whatever, this would be a more complicated polynomial function. But the degree is going to be 4 because if you have an x squared term, you have an x minus 2 term, and you have an x plus 2 term. If you were to multiply that out, that highest degree term would be x to the 4th. So at the ends, it definitely behaves like they all behave the same. If you look at these, every single one of these, both ends are pointing in the same direction and both pointing up, right? And that's because they don't have a negative out in front that's doing the reflecting. So at the ends, they behave the same. But what's happening in the middle is there are lots of twists and turns in there. So let's go ahead and answer the questions for this one. How many distinct factors? Well, I see x squared, I see x minus 2, I see x plus 2. There's 3 distinct factors. The intercepts, it crosses at -2. I can see it crosses at 0, and it also crosses at 2. So there are 3 x-intercepts. And it says, are they tangent to or do they cross? Well, the only one that's tangent to, this one right here, is tangent to. So that one is tangent to. The other 2 just cross. These cross. Yeah, it's going to be hard to fit that in there. But this one, you can just say, just maybe put a C next to it for cross, and this one cross. But that one there in the middle there, that graph comes up, touches it, and turns right back around and stays below the x-axis. That's considered tangent there. And again, that means it's going to account for more of the possible solutions. It's almost like it creates a little parabola that's facing down right in here. So like this part right here is like a little parabola, and parabolas many times will have 2 solutions. So it's like a little parabola there. How many turning points? Well, if you look, there's 1, 2, 3 turning points there. You can see each, there's one there, there's one that I circled there, and there's one I circled here. So they're going from either increasing to decreasing or vice versa. So when I look at how many global maximum values or local maximum values, there are no global maximums because this thing goes up forever, right? But local, there is a local one, and it's up here. So this one's a local right there, and there's one. And then there's actually 2 minimums that look to be exactly the same. So we'd have to know for sure, but it looks to me like there's 2 global minimums, okay, which is unusual. I mean, usually it's like you can't have 2 absolutes of something, right? But because they're the same, we can just put like same. Okay, and there's local, there's none. Okay, so those are like the absolute lowest it ever gets. All right, and then the final graph. Okay, so you can tell as they start to get more and more factors, and if you expand that out, it would be an even more and more complicated polynomial function. You're going to get more twists and turns, more unusual kind of graphs. Again, though, we're still looking at, if we look at the very far left and the right, this still looks like the most basic x to the 4th graph, right? There's a lot of bends and turns in the middle. Okay, but at the ends, they both point up. So As far as how many distinct factors, you can see there's 4 listed. 1, 2, 3, there's 4 listed factors. And if you look at the x-intercepts, what are they? Well, these are scale by 2s because I had to zoom out a little bit to get that lowest point there. But one's at -3, the next one crosses at -2. Then you can see it crosses through at the origin at 0, and then it crosses at 2. And again, that correlates with those factors. If you take each one and set them equal to 0, you can see that -3, -2, 0, and 2 are the solutions. None of these graphs are tangent. They all cross. So all cross through, no tangent ones. So they all count as really just one solution. How many turning points? I see 1, 2, 3 turning points. And actually that is the most that you could possibly have for this 4th degree polynomial. That's as many twists and turns as you can have is 3. So it's it can up to 1 less than the degree. So you've seen it does 3 and 1. So this is possible to as long as you don't go you stay under the degree. That's how many twists and turns the graph can have. So let's see, global max or local max. So the global max, there's none, because again this continues up forever on the ends. That's never going to get to a highest point. But there is a relative or local maximum right there at that point I just circled. So local, there's 1. And we could, there's a way that we could figure out what that was. You can use the graphing calculator to do that, but in this case we just want to know how many. And so that one's a local. And then minimum values. There's actually one minimum that is local. So this one's a local minimum right here. And then this is a global minimum right here, because that's as low as it absolutely gets. So there's one global or absolute, and there's one local minimum. Okay, so now it's actually time to do some graphs. And this is probably compared to the lesson so far will be much quicker, just because, you know, now we've got a lot of baseline information. We've learned a lot about the characteristics of some of these graphs, and now we're going to put them into play to sketch these graphs. So given a polynomial function in intercept form, so that means that it's going to be in that like factored form, you can sketch the function's graph by using the end behavior, the x-intercepts, and the sign of the function values on intervals determined by the x-intercepts. The sign of the function values tell you whether the graph is above or below the x-axis on a particular interval. And you can find the sign of the function's values by determining the sign of each factor and recognizing that the sign of the product of those factors is. So we're going to take that and put that all into play to do some graphs. So the first function we're going to look at is x times x plus 2 times x minus 3. Now, not that we want to do this each time, but just to give you an idea of what this looks like in expanded form. I went ahead and multiplied it out. So this would be x cubed minus x squared minus 6x. I just FOILed the x plus 2 and x minus 3 and then distributed the x through. So this is what it would look like in expanded form, but we like to use factored form to graph it because this is going to tell us a lot about the graph. Remember, it's going to tell us that this is going to cross at what makes that 0, which is 0, at what makes this 0, which is -2, and what makes this 0, which is +3. So if I could come down here, I could put this on the graph at +3, it's going to cross at 0, and it's going to cross at -2. When I think about what this graph would look like in terms of the ends, for the end behavior, I actually know that because this would be a cubic function and there's no negative out in front to say it's reflecting, I know that the ends are going to behave like this. On the right hand side it's going to face up, and on the left hand side it's going to face downward. So I know that going to the left, eventually the graph is going to have to continue down forever, and on the right it's going to have to continue up forever. So as x is approaching positive infinity, it's going to approach positive infinity, in other words, and then towards negative infinity on the left. So we identified the graph's x-intercepts and then used the sign of f of x on intervals determined by the x-intercepts to find where the graph is above and x is where it's below. Okay, so I know if it's going to be down here on the left and up here on the right, that what's going to have to happen is this thing's going to come up cross here. It's going to, I don't know how high up it goes yet. I'll figure that out in a minute. Then it's going to have to turn around and pass through the x-axis again. Then it's going to have to go down, I don't know how low, eventually, but then it'll go up again. So maybe something like that. Now that would be kind of really like broad. I guess that would be like a general sketch of the graph because we at least know how it's going to end and where it's going to cross. But if we want to get a better idea of that, this is where we can bring in our graphing calculator. We could do that, or if we didn't have access to that, like sometimes some courses they don't allow you to use a graphing calculator, you could use another strategy. So what I could do is I could say, well, I know it's going to cross at -2 and at 0. So what about if I plugged -1 in? So let's say I took and put in for x -1. So what I'm going to do is put in -1 here, which is between, right? I'm going to put in a point between these two. And if I do that, let's say I get -1 times -1 plus 2 is 1, and then -1 minus 4 is, or minus 3 is -4. If I multiply those together, I'd get +4. So actually there's the ordered pair, -1, 4 is on that graph. So that means 1, 2, 3, 4. I actually could put that point on the graph, so I know here it's going to look like this. It's going to get, now I don't know if that's the highest point. It's halfway in the middle. It might be. So if I didn't have a graphing calculator, that would be at least better than nothing, right? And if I did have a graphing calculator, what I could do is graph this function, and then I could calculate that maximum, which we'll talk about when we're in class. I'll show you how to do that. But for, so we could do this, or we could, let's see, we can plug values in, or we can calculate a maximum using the graphing calculator. Okay, so now I know it's going to kind of look like this on this side. Now I also have a 0 over here at 3, right? So between 0 and 3, say if I split halfway, or maybe I plug in 2, I mean, we don't really know, but let's, if we want to choose halfway point, we could plug in 1.5 in instead. So now I go here and put 1.5 in. This would be harder to do without a calculator. I could put 1.5 in here, and then 1.5 in for, let's see, 1.5, and then 1.5 in here, and then, I mean, at least you'll always probably have a scientific calculator, even if you don't have a graphing calculator. So again, I know this was -1 and 4, and then for this one, let's see, I got 1.5 times 1.5 plus 2 is 3.5. So 1.5 times 3.5, and then that's 1.5 minus 3.5, which is -1.5 times -1.5, and I get, let's see, -7.875. So I also have a point at 1.5 and -7.875. So then I could come down here, 1, 2, 3, 4, 5, 6, 7, 8, and I know that halfway between these, I have a point down here at, maybe just below here, like, wait, 1, 2, 3, 4, 5, 6, 7, 8, just above that right there. So then I know I could go like this, and it would go up like that. So that really is a very accurate graph. It doesn't probably look significantly better than the first sketch I made, because I was kind of just estimating how high I thought it. I mean, maybe between these zeros it goes up significantly higher, significantly lower, but definitely being able to plug a point in between each 0 is going to give us a much more accurate graph. Or if we could perhaps calculate a maximum or minimum, if we could actually see this graph on the graphing calculator, we could calculate the maximum and then get a very accurate graph. Okay, let's try another one. So it says sketch. Oh, actually, let's switch over here. There we go. So sketch the graph of the polynomial function. So let's see, we've got opposite of, or negative, x minus 4, x minus 1, x plus 1, and x plus 2. Well, the negative out in front tells me that because, and if I actually expanded this out, I'll tell you what this looks like. And I got, when I multiplied this out, I got negative x to the 4th plus 2x cubed plus 9x squared minus 2x minus 8. So I just FOILed these out, and then these out, and then I multiplied those together, and then took the opposite of everything. Now, you don't have to do this to be able to graph these, so I just wanted to give you an idea of what this, how complicated this function looks like, and now why the graph's going to be quite complicated as well. But in factored form, or in this intercepts form, we can see that this actually crosses the x-axis at 4, which is what makes this one 0, right? And then at 1, it crosses at negative 1, which is what this one makes this one 0, and then negative 2. So it's going to cross 4 different times. But because that leading term is negative x to the 4th, it's like it's going to be one of those x to the 4th graphs facing down, which means at the ends it's going to look like this, because we looked at those there's going to be a lot of bends and turns, like in the middle, like this, right? But at the end of the day, or at the end of the grass, I guess, would be both facing down. So both are going to go towards negative infinity. So that's going to help if we want to just get a sketch. They go to negative infinity, because I know the graph's going to cross here at 4. It's going to cross at 1. It's going to cross at negative 1, and it's going to cross at negative 2. And then ultimately it's going to face down both spots. So maybe it kind of goes up, it crosses here at 2, comes up here, comes back down, maybe goes like this, then ultimately goes down, right? To know like exactly how high here it goes, how low here it goes, how high up here it goes, this is where we could plug in some numbers into that. Or we could use our graphing calculator and look at it, and either the table or calculate the maximum or minimum values. Which, again, when we are in class together, I can kind of show you how we could make these more accurate. But to find a pretty accurate one, even with just this information and just some simple calculations, we could plug in numbers between negative 2 and negative 1. We could plug that in. We could plug a number in between negative 1 and 1. We could plug a number in between 1 and 4 and get an idea. So for now, because it does say get a sketch, and we'll try to come back and revisit this graph when we're together, and I can show you some things using the graphing calculator. But otherwise, we're just going to say, okay, well, it's going to start down low, then it's going to come up. We don't exactly know how high, but it's going to come over the top, come down, kind of loop around here, come back up. Maybe it goes up a little higher, I don't know for sure. Again, I'm just kind of estimating. And ultimately, both ends are going to face down. It's going to cross those 4 times, and that would be a pretty good sketch. Now, this doesn't have specific points between the other 2 points, but it does say sketch. So if I ask for a little more accurate graph, I would say, include points between your x-intercepts or your zeros, or I would say calculate the local or global maximum and minimums between there. But for now, because it does say it's a sketch, that's a reasonable sketch to come up with given this information. Let's try one more. Okay, so expanding this one out, because that's a negative x squared that I'm going to distribute through, that would be negative x cubed, and then negative x squared times negative 4 would be plus 4x squared. So the dominating power, that highest degree, is 3, and it starts off with a negative. So I know that the end behavior, normally a cubic function goes like this, right? But I know because this is a reflection now, it's going to go like this. So I know that my ends, one's going to face up on the left, so the end behavior is going to face up on the left, and it's going to face down on the right. So we kind of know that it might have a little bend and turn in here a little more, maybe like this here. We don't know for sure, but we do know on the ends what's going to happen. So now we can take, we know that the intercepts are, let's see, what makes that negative x squared equal to 0, right? If we just say what's negative x squared equal to 0, we know that that's going to be 0. So x is going to be 0. That's one of the x-intercepts. It's going to cross here. And then the other one is when x is 4. So it's going to cross at 4. It's only going to cross twice. Okay. And so then we know on the one end it's going to be coming down like here, like that. But then on this end it's going to go down. So how is that going to happen if this dips below? It would have to cross again, right? So it can't do that because there's no other intercept, right? So what that means is this is going to kind of just loop around here at 0, and then it's going to come up to a certain height, I don't really know what, and then it's going to cross through like that. So this is one of those ones because when we have a term like an x squared or an x cubed or whatever, that's actually producing one of those zeros that's tangent to the x-axis. Actually, if it's just x squared or x to the 4th, so if it's an even exponent on that, it's going to kind of create almost like a little parabola right near that 0. So again, you can put this in your graphing calculator and you can get an idea of that this is what it's going to look like, and then you can get a much better idea of exactly how high this point is right here. Now that would be a local maximum. This would be a local minimum. There are no global max or mins on this graph because the ends go up and down forever. Okay, so this is a very long lesson, and at this point we're going to end the class, and we'll pick up when we see each other together in class, and we'll explain to you the modeling of a polynomial function, and we'll talk more about how we can even improve our graphs using a graphing calculator, and how we can use the graphing calculator to approximate or calculate global and local maximum and minimums, which is what we'll need to be able to complete this modeling question. So we're going to wrap up the lesson video here, and we'll continue when I see you in class.